It is a great pleasure to be here, seeing all this high power, all these brains in this committee. So I'm going to talk about something totally different from what you have been talking about. According to Gell-Mann, this is basically, it's called squalic physics, okay? That's condensed physics. But I understand that Professor Young at one time also worked on it, and off-diagonal long-range order on the quantum fluid and also the quantization of flux. So therefore, I feel it's okay. So I can talk about this, and that's the area I'm working on. First thing is, what I'm going to do is going to talk about the long march to a higher TC, briefly summarize what has happened. And for example, in 1911, it was discovered until 1987. And that period, usually in our field, we call it low temperature superconducting period, and basically concentrated on the intermetallic compounds. The TC goes from 4.2 to 23.2 degrees Kelvin. And then later on, we get into the so-called high temperature superconducting period and dominated by cuprates with a transition temperature from 35 degrees all the way up to 164 degrees Kelvin. And then later on, through in the year of 2006, a new class of material was discovered by Hosanna and co-worker, and it's basically concentrated on iron niptides and chalcogenides, and the transition temperature goes from 26 to 100 degrees Kelvin. And then, of course, what happened recently is the announcement by the German, and that is on hydrides with the transition temperature up to 190 degrees Kelvin, but under extremely high pressure. And then I'll conclude my talk. Ever since the discovery of superconductivity, there are several questions. What, at the beginning, that is, what is this phenomena and how it happens, and where can people find more of this kind of materials? And of course, people immediately realize the potential of applications, and therefore where to think about this. So superconductivity is an area in our field, we call it, it's a 104-year young, vibrant subject. And it has lured numerous great minds in physics to try to figure out what's going on in this subject. It has also humbled many of them, and this was summarized in an article. It's called Failed Theories of Superconductivity by Jörg Smalling from Ames Lab, and published just at the 50th anniversary of BCS theory. As you can see, all these great minds, and these are the people try to solve the problem, and before Meissen Effect was discovered in 1934, and then after the development of quantum mechanics, and this group of people try to solve the problems, as you can see here. For example, when Einstein looked into this problem, and he thought this may be due to some molecular conduction chains. So therefore, he thought all these superconducting currents are different from the nuclei, so flows in different directions. So therefore, in order to test his model, it was very quick. And Camelon owners just got two strips of different materials, put it together, and see whether supercurrent flowed across different material. It turns out it did. So therefore, that model immediately was killed. And then, of course, J.J. Thomson talking about fluctuating electric dipole chains. And then Camelon's owners, even himself, thought superconductivity actually happened within the filaments in the materials. Felix Bloch and Landau talk about spontaneous current approach, and Bohr and Kronig and talk about coherent electron lattice motion. Actually, this last one is similar to what people talk about the charge density wave. So superconductivity is a very simple phenomenon, as it can be summarized in the following way. First, the disappearance of electrical resistivity that led to Camelon's owner's discovery of this phenomenon. And that is when resistivity, when you cool down the material, the resistivity drops as a metal should, and therefore all of a sudden it drops to zero, and this is called the critical temperature. And then the other properties is complete expulsion of our externally applied magnetic field. That is known as the Meissen Effect, discovered by Meissen and Oceanfeld back in 1933. As you can see, because of these properties, you have a superconductor at the bottom here, and then you have magnet on top of it. And actually, the magnetic field cannot penetrate. As a result, it flows on top of it freely without friction. And the third property is so-called macroscopic quantum phenomenon. We know usually in those days, in order to see the quantum effect, usually people try to shrink themselves to very small size and get into the interior of an atom and look at the electron and try to determine how the electron moves. We know the movement of the electrons cannot be described by Newtonian mechanics, and it has to be described by quantum mechanics. But superconductor is a macroscopic, it's a large object. You can feel it, you can touch it, and therefore the phenomenon is quantum phenomenon, and that's why people call it macroscopic quantum phenomenon. Because of these three properties, the first property gives us the possibility of using the material to generate electricity, transmit electricity, and store electricity without loss. And the second properties give us the possibility of building very efficient electromechanical machinery. And the third property gives us the possibility of building ultra-fast and ultra-sensitive devices. And so those are in order to have these properties, one has to overcome three parameters. Or three barriers. The temperature barrier, that is, the temperature has to be lower than the critical temperature, T sub C. And then the current density going through the material has to be lower than J sub C. And then the critical field that the material can be exposed to has to be lower than the so-called critical field. So at the beginning, people try to figure out why this whole thing happens. And of course, the crucial development later on in 1956, and that is Leon Cooper proposed, I believe Leon Cooper was a former postdoc of Professor Young, right? Yeah, a postdoc of Professor Young. And so he actually proposed two electrons can form pairs as long as there's an attraction between them. We all know that electrons should repel from each other. And if you can find a way so they can attract from each other, then they immediately condense to a lower state, okay? And how to get that little attractive interaction, and one of the things proposed is a so-called electron-photon interaction. That is when an electron comes in, it polarizes the lattice. As a result, this area has a net positive charge. And when the first electron continues to move out this region, and the second electron is rushing through this area at a higher speed, and therefore to the first electron as if there exists a net attractive interaction between the two electrons. It's because of this little net attraction, therefore they form pairs. And this is the crucial thing. And then a year later, Bardeen, Cooper, and Schrieffer developed this famous BCS theory. I think in 2006, Rick Smalley pointed out the humanity's top 10 problems for the next 50 years. The first thing he listed here was the energy problems and many others like water and so on, environmental terrorism and all these things. It turns out one of the most crucial problems is energy. If we have sufficient energy, actually we can solve many of these problems. So water, we can desalination, like what Singapore is doing, and many other things, can be solved. Food, you have energy, you can produce it. Environmental, you can use energy to clean it up. So lots of things. So energy is the most crucial factors in all these problems. If we can solve it, we can solve the rest of them. It turns out the most environmentally friendly secondary energy source is electricity. I call it secondary energy source. It's not primary. In order to get electricity, you have to start off some other things, okay? Either some others like chemical or basically chemical like fossil fuels and so on. And then we look at the Asia map at night, and you can see here, and there are some bright spots. Of course, Japan is here, and South Korea is here, and China, Beijing is here, Taiwan is here, Hong Kong is here, I think Singapore is here, okay? They're all bright. But all of a sudden, you can, so that tells us wherever there is light, that is electricity, there is prosperity over there. We can find out what happened here. That's North Korea, okay? It clearly tells you that's the problem here. And then the most efficient electricity carrier, turns out, is superconductors, because it can carry electricity without loss, as I mentioned earlier. So to search for superconductors for all these years with higher TC was one of the driving force for the sustainable research, R&D in superconductivity research. And basically is to save more energy and make more efficient use of energy. So for example, if we want to use a superconducting device, and first, to save energy, let's assume we can save so much energy, and in the same time, but the problem is to cool it, in order to get it to a superconducting state, we have to cool it. So therefore, we have to use so much energy. So in order to do that, so even for the LTS, the low temperature superconductors, we may need more energy to cool it than the energy we can save here. So therefore, we like to increase the superconducting transition temperature and to use less energy to cool it. And therefore, we have a net gain of energy here. That's what we save. If we continue to raise the transition temperature, we save more and more energy. For example, even the present high temperature superconductors, when we use it, we can really save quite a bit of energy. But the ideal case is to get a superconductor with the transition temperature up to room temperature. Then all the energy the superconducting device save can all be real safe in that case. And that's the goal for many of the people in my field try to achieve. The general principle for superconductivity to occurs, as I already mentioned, and that is it needs electron pairing, and then the second thing is phase coherence, as described in the BCS theory. The second thing, the electron pairing requires an effective attraction, as I just mentioned, and then therefore it's basically attraction between them. What I mentioned, the mechanism is the exchange of phonons. That's what we do. At higher temperature, the thermal fluctuation excitement increases, and as a result, if the thermal excitation energy exceeds the pairing energy, the pairs breaks up and superconductivity disappears. So higher TC needs greater pairing potential. But then unfortunately, when you have a greater pairing potential, it can induce some kinds of instabilities and even catastrophic instability. In other words, the material may not even exist. So therefore, the challenge to raise the TC is to enhance the pairing potential without triggering catastrophic instabilities. So to raise TC before 1986, and there are two basic approaches. The first, we call it Matthias empirical approach. Basically, he just looked at the electron, the valence electron per atoms. And he found out the highest TC usually occurs in two places. One is it's 4.75, and the other is 6.4, in here, so two peaks. That means when you have the electron counts, per atom counts with that, doesn't guarantee your higher TC, but the highest TC occurs in these two numbers. One is 4.75 and the other is 6.4. It works well for crystalline intermetallic materials, but does not work for amorphous materials nor oxides. The second approach is the BCS rational approach based on this simple expression. That is, TC is proportional to the characteristic temperature in this case because the electron phonons, so therefore it's the bitemperature, exponential minus 1 over mv. N is the density of state, and V is the attractive interaction. So to raise the TC according to this formula is very simple. We just increase the bitemperature, density of state, and attractive interaction. it turns out all these parameters are coupled to each other, and so that makes it a little bit hard. And this formula has described superconductivity very well, but it cannot predict the TC. So therefore, in the 80s, people were very happy because TC continues to increase, and then new physics generates. The government puts money in, so we all smiled. But in 1980s, late 80s, the situation changed because TC did not go up anywhere, and then the government cut the funding, so people were not very happy during that period of time. So TC before, the situation before 1986 can be summarized here. You look at TC as a function of time, it basically goes like this, all intermetallic material elements here. The people's goal at that time is to reach 77 degrees Kelvin. That is the liquid nitrogen temperature. By extrapolation, it takes many, many years, not until 2200, before people can reach that. And it turns out experimentally, people couldn't get it so high. The highest experimentally reached temperature is 23.2 degrees. And theoretically, people predicted 30s should be the limit. So therefore, the most serious crisis at that time is the so-called confidence crisis. Then we look into the cause of confidence crisis, because basically the major thing is lattice instability. As I mentioned before, you try to get strong electron-photon interaction, the lattice has to be soft. When it softens to such an extent, the lattice collapses, okay? That's catastrophic instabilities. So it's lattice limits. So at that time, we decided to look into it using high pressure to determine whether this is indeed the stopper, okay, for us to go higher. Because at that time, when we look at the so-called high TC, like niobium-13 and V3Si, those A15 compounds, when you cool it down, before it gets into superconducting state, indeed, it undergoes a lattice instability and transformation. So we decided to control this lattice instability by the application of pressure and try to see whether TC indeed can be raised if we can suppress this instability. So what we did is, together with my student, Vic Diachenko, as you can see, we take the V3Sis as an example. When you cool it down to 21.5 degrees, it undergoes a lattice instability, a structure transformation, and then becomes superconducting at around 17 degrees here. So we apply pressure, and we can suppress this instability down. And then when it goes up to 18, 19 degrees, it's completely suppressed. And TC, indeed, TC increases when we suppress the instability, when it gets closer and closer. But then later on, after the suppression, the lattice instability, the transformation temperature is suppressed below the superconducting state, and the slope changes, okay? The TC slope changes. So therefore, one can do the following, and you can see, where's the cursor? Okay. And so therefore, we can interpolate back to zero pressure. And you can see with instability, the TC is approximately 17 degrees. And then when you, 16.4 degrees or 3 degrees. And when you suppress the instability, the TC is only 16.9 degrees. So therefore, from this study, we immediately realize, that it should not be the killer for higher TC. It only affects transition temperature a few tenths of degrees. It's not the major things. So that gave us lots of confidence. And therefore, of course, at that time, we were also looking at the oxides. But Alex Miller and George Batnos published this paper and saying possible high TC superconductivity in the barium lead copper oxide. This is a perovskite-like transition. Essentially, they dope the lanthanum, so-called 214 compounds, but they use a different composition and then get a record TC of 35 degrees Kelvin. And the paper initially was greeted with skepticism by most except a few groups, because usually superconductivity was supposed to happen in metals, and this oxides, the oxide is supposed to be insulated, not even metallic, let alone superconductivity with high TC. So the first thing, turns out, as I mentioned at the time, there were only 4 groups believe in them. first of Tokyo group. Tokyo groups, actually, they have the postdoc working in the in the Zurich group. So of course they will believe it. And our group, because we were looking for a long time, but we did not get it. IBM group, because Miller and Bennos came from the IBM lab, Zurich lab, so IBM group believe in it. And then Beijing group by Zhao Zhongxian and so on also believe in that. So immediately, very quickly, we confirm their results in late November, and we obtain more. So once we reproduce their results, in fact, I dropped Alex Miller and George Bennos notes. That's on December the 3rd, telling them we reproduce their results and we believe the temperature will continue to go up. And Alex Miller actually called me up and said to thank me, because at that time, lots of pressure on them, whether that's true or not. And also comment later on me, to me, they said, I couldn't believe you're he thought I was optimistic, because at that time I felt TC should go up to 77 degrees for sure at that time. So the reason for that is that we reproduce the results, we immediately apply pressure to it, we get the temperature about 40 degrees. I'll tell you at that time, people were very cautious. For example, the chief editor was Myron Strongen of PRL, actually suggested me to change the title, okay? Originally, I said superconductivity about 40 degrees, and he said, why don't you make it softening, instead call it evidence for superconductivity, and so on, okay? And then also my abstract, he proposed to change it. Instead of talking a superconducting transition and so on, why don't you say an apparent superconducting transition? So you can see at the beginning, people were very cautious. And then after we raise it to 40 degrees, that above the theoretically predicted value. But then the next thing is still close to the theoretically predicted value of 430 degrees. So we decided to continue to raise the temperature by the application of pressure to 52.5 degrees Kelvin. With that, immediately, there's no doubt in our mind that the theoretical prediction or the assumption based on which the theoretical prediction of a ceiling of 30 degrees needs to be re-examined. And by the application, we realized the TC was raised at an unprecedentedly high rate, and therefore it tells us this class of material must have some, it's very different from the conventional class of superconductors, and it's worth further study. So because pressure raised the TC and so on, so we proposed to do chemical substitution. And that includes, for example, replace the barium by strontium and calcium. At the beginning, by strontium, TC goes up. That was very nice, but unfortunately, when we replace it with the smaller elements like calcium, TC goes back down. So then we also look into the other element, lanthanum. We can replace it with some smaller trivalence elements. Of course, usually that's rare earth material. They are all magnetic at the time. We thought magnetism usually works against superconductivity. So at the time, we proposed to use yttrium and lutetium and so on. So it was interesting when all this happened, the university made a press release, and it appears on December 31st, in the New York Times. And because Walt Sullivan called me up, I think on the 30th. So at that time, my wife was vacationing in Boston. I told my wife, May, look it up, see whether it's in New York Times or not. Then later on, that morning, she purchased a copy of New York Times and called me back. She could not find anything about this thing. I said, did you look at everything? She said, yes, I did. I looked from the last page, all the way up, didn't see it. I said, did you look at front page? She said, no, I did not. So it turns out I was on the front page. Okay? So the reason we were optimistic was back in the 11/25, and that's a day before the Thanksgiving, 1986. Actually, we already detected the resistivity drops starting about 70 degrees. And that's why we were so optimistic about it. This turns out it's really the first sign of superconductivity above, slightly below 77 degrees was detected in a multi-phase sample, but not in the pure 214 compound. 214 compound was identified by Kitazawa and Tanaka in Japan at the time from Miller and Benno's sample. And so in our case, what we do is the following. We decided to grow pure 214 material. Usually in physics, we like to get single crystal to study it, but we failed. I'm not the expert in single crystal growing. So we destroyed 2/3 of our capability of growing single crystal. So we decided to take a different approach. We say, why don't we focus on the really high TC phase instead of the 214 phase? So then this later on, we did the magnetic measurements and on January 12, 1986. And indeed, we saw Meissen effect starting at around 100 degrees Kelvin. So that was sure that superconductivity above 77 degrees will take place. And the problem is how to stabilize it. And then later on, and later on, when we go back and look at the structure of this compound, this is a mixed phase compound, and turns out the lanthanum barium copper oxide 1,2,3 phase, it's there, but at the time we did not recognize it. And then later on January the 29th, 1987, my student, M.K. Wu, that we collaborate with, and Colin, he did stabilize the YBCO with a TC above 77 degrees. At that time, one of the challenges to do this kind of research is to make sure the temperature is correct. Because prior to that time, our thermometer can only measure temperature below 23 degrees. Here was so high, we were not sure it's correct. So therefore, in order to be sure, this measurement was done in a bottle of liquid nitrogen. So therefore, it cools down to this point. There was no doubt it's above 77 degrees. Then resistivity was done. Then we immediately did the magnetization measurement and showed the Meissen effect. There's no doubt in our mind that superconductivity above 77 degrees was finally stabilized. And this material is the first stable liquid nitrogen temperature superconductor. And done by this two group of people, my group at Houston and M.K. Wu's group at UAH, University of Alabama at Huntsville. Again, this news was leaked out. So S. Sullivan reported it on the front page of February 16, 1987. It's interesting. This was just 50 years before New York Times reported Young's non-conservation of parity, basic concept in physics, is reported upset in tests, okay? So 30 years later, not exactly, but close. So later on, this results was reported at Physical Review Letters, and as shown here. So it was, yesterday I mentioned this paper. Before that, I told M.K. Wu we tried to write one sentence paper, but turns out we did not have the courage of doing that. So this appeared on March the 2nd, and March 2nd, 1987, particularly for those people in Texas, we consider that's a super day for physics. The reason is 90 degree superconductivity and supernova, and also announced, and then at that time, we were talking about the construction of superconducting super collider, in Texas. So then came the 1987, as I already mentioned earlier, and we, together with Bob Hayes and Geophysical Lab, determined the structure, and then we do some testing. Immediately, we discover a whole series of compounds very quickly, and this of the same structure. And that's the origin of the so-called Woodstock of physics on March the 18th in 1987. thousands of people rushing in to listen to these results. And this is Alex Miller and Tanaka, Soji and Tanaka there. And then even the great communicator, Reagan, with his cabinet member, tried to see magnetic levitation, and as done by the then director of Argonne National Lab. So following that, there are some other developments following the similar path, and then a bismuth-based high-temperature superconducting material system was discovered in 1988 with a TC up to 110 degrees Kelvin, and then very quickly, and in the United States by Sun Zhenzhi and L. Herman, they found a thallium-based material with TC 125K, and then later on in Zurich, and Arts and co-workers found a mercury-based material with TC up to 134 degrees, and then by the application of pressure, we raised the transition temperature up to 164 degrees, which was the record until very recently on superconductor. And later on, I was looking at that thinking. And later on, of course, in the year of 2008, Hosanna and co-worker found a new class of material with TC up to 57 degrees Kelvin. So these are all plotted here. Because of time, I'm not going to go through all this in details. So many HTS, because of this development, many HTS, high-temperature superconducting prototype devices have been made and tested with superior performance than their non-superconducting counterparts. You can see that wires and tape and cables were made for this high-temperature superconducting materials. Based on this, lots of devices were built here for magnetic imaging, and including cardiovascular imaging, MCG, and this is for energy saving, and flywheel, and this motor, and this current limiter to control the quality of the grid system. And my colleague also developed a system to detect cancer noodles in the body doing that. And this is the generator, a motor developed by American Superconductor for the Navy and many others. And I even put this magnetic levitating train in Japan here, although this was built based on the low temperature superconducting material. But now there's talk try to get it into high temperature superconductor material to do it. And this is just to show you one of the impressive things in magnetic imaging. For example, here when you try to image the spinal cord injury of a rat, so what you do is you have to implant the copper coil sensor underneath the skin on the poor mice, and therefore, when you take the imaging, it's not very good as indicated here, the copper. But then when you use superconducting material, and you only have to cool it from the top, the sensor is inside this styrofoam cup, and then you can see the quality of the image is tremendously improved, even detect the brain and all that. So YBCO turns out it's the first liquid nitrogen superconductor, and it's a quality, it can be used to make wire. It's very robust. It can make thin film, epitaxial thin film for microelectronic devices. It has high GC and high irreversibility line, about 77 degrees. So therefore, it remains to be the best material for high temperature superconducting science and technology. So therefore, in the year of 2000, it was included in this new millennium time capsule as chaired by Hillary Clinton. While this is all going well, and then Bart and Marx of Max Planck Institute analyzed the superconducting science publication statistics, so-called scientometrically in 2006, and sentenced high temperatures the superconductivity to die in the years of 2010 and 15 by extrapolation, as you can see here. So it turns out once they announced that in 2006, then in 2008, Hosono and co-worker in Japan found a new class of material. It's an iron-based material with TC, very 26 degrees Kelvin. And very quickly after that announcement, a group of scientists in Japan, in China raised the temperature very rapidly to about 50s degrees to 50s. And now with that development, people start asking, is room temperature superconductivity achievable at the time? At least just thinking philosophically, at this moment, there's no evidence, experimental or theoretical, that prevents room temperature superconductivity from happening. Whatever physics law does not say won't happen, will happen. That's what we have learned. And then room temperature superconductivity will be the next grand challenges in superconductivity research as announced by Department of Energy and also Air Force Research Office. As we know yesterday, that the next generation of accelerator in this field, in high energy field, probably will depend on the success of high temperature superconductivity research. But the question is how and where to find it, okay? So yeah, you can find it in Hollywood, okay? I think this is a room temperature superconductor. You see this magnetic levitation at room temperature. And in the film, it's Avatar by James Cameron in 2009, as you can see here. Okay? So in order to find this, actually, we have thought about it, and it was announced, which we decided the holistic, multidisciplinary, enlightened empirical approach, and it's important, it's the best approach, because we consider knowledge, imagination, experience, courage, and luck all play an important role. So the TC record, unfortunately, has stagnated at 164 degrees Kelvin since 1994. Is it time for us to look into the new direction, you know? So recently, there were three unusual observations. One happens in the iron-based material. The TC can be, this material was not supposed to be superconducting, but when you dope it with a little bit rare earth, you can get it up to 49. It's not a big deal, but then it's in single crystal, and therefore the superconductivity is non-bulk in a single crystal. And then in iron selenide, as done by Seach and co-worker, they found that single layer material will have a temperature at the beginning around 40s and then later raised to 100 degrees Kelvin. And then, of course, the recent announcement of H2S under pressure up to 200 gigapascal, superconducting up to very high. So we did all kinds of study. Because of time, I'll just briefly mention it. The 49 degree superconductivity is very unusual, and therefore it's consistent with the so-called interface enhanced superconductivity. So therefore, its superconductivity may be found in these single crystals. And then the other is Seach results on this. And they announced it goes very high. The transition temperature originally is something 40 degrees. But unfortunately, in that case, the material was done basically using tunneling method. And they saw energy gap. Whether the gap really, they saw a gap exist up to 60 degrees Kelvin by different people in China. And now the question is that gap really superconducting or not? And one of the definitive signature of superconductivity is the Meissen Effect. So therefore, we decided to look at the Meissen Effect. Indeed, we saw the Meissen Effect in this material. As you can see in this magnetization as a function of field measurement. I'm not going to bother you with the details. So it is superconducting, but that Meissen Effect only exists below 20 degrees Kelvin approximately. And then up to 45 degrees Kelvin, we saw macroscopic superconducting states exist in this material. And we also saw collective excitations exist up to 100 K. And so the nature is not yet clear. In their announcement, they said one layer is superconducting, two layers not superconducting. Our experiments at this moment cannot determine that question. The most exciting recent announcement was the so-called conventional superconductivity at 190 degrees at high pressure by Aramats and co-workers from Max Planck Institute in Mainz. And you can see here under the pressure, and the material undergoes a phase transition into a metallic state. When you increase the pressure further and further, finally the temperature goes up to 190 degrees Kelvin. And then in order to show that this is superconductivity, they, instead of, in addition to H2S, they also look at deuterium. And they saw that deuterium sulfur, the transition temperature goes down. That's Meissen effect, isotope effect expected, if electron-phonon interaction. They apply a magnetic field, they can see the transition actually suppressed down. So all this, they concluded it must be a superconducting transition. But the interesting thing is that according to BCS theory, the TC is proportional to isotopic mass minus alpha. Alpha should be 0.5. In this case, it's around 12 or 13, depending which transition you're looking at. It also looks like a type 1 superconductor because all those curves are suppressed in parallel. You can see in field in parallel. In this case, in parallel. Usually at high TC, you have flux pinning. It should be broadened instead of in parallel. So this is another question we don't understand in this case. And it's also history dependence. It's not you apply pressure, it becomes superconducting. You have to cycle it a little bit, and what's the reason? And there's no magnetic signature done at this moment. So what's the reason? Now, the implication of this, if it is true, it will change lots of things here. I'll come back to this slides if I have time in here. And so the TC now is up to this point where we continue to go up. Based on the trend, it looks like it may go up, but we have to change everything. The other thing is to address this issue. One is that, as I mentioned in one of them, interfacial superconductivity, and then the other is the recent announcement really a superconductor transition. On those things, we are doing 2 experiments, essentially to look at interfacial effect microscopically and try to do this. You grow the material in the MBE chamber in situ, and then you continue to take it out to do STM, microscopic measurements here, and then later on do macroscopic measurements in the rate. This is an integrated system that we're building at this moment. The other thing is try to see whether we can do magnetic measurement on this material under extremely high pressure. And this is the little cells that aromats use to generate that high pressure. It's a little guy here, okay? That little cell over there. And the sample is locked inside here. So we try to see whether we can determine the magnetic transition in this material. So what we have done first, we put a piece of lead in there of the same size of the sample, similar size of the sample, and see whether we can detect the signal and to 10 to the minus 8 in our system. Indeed, we can see the transition, as you can see here. So we believe in about a month, we should be settled with this question. And the search for higher TC will go on. It appears to me that nature has been kinder to physicists than to mountaineers. Just like to high energy physicists, there's no end in the scale of energy. It can continue to go up. And this kinder to physicists than to mountaineers, to whom the final goal of Mount Everest was already granted and reached, and the excitement ceased once they got there, okay? So you look at this was done in 1953, but even that, still lots of people trying to climb Everest, okay? So with that, I thank you for your attention.
Thank you very much, Paul. I think we have time for a few questions.
Yeah.
You mentioned the critical magnetic field and the critical current density.
Right.
With high TC, what happens to the other two? With
Oh, yes.
HC?
So far, they are very high. But of course, according to physics law, when the TC gets higher and higher, the coherence length will come down, So therefore, some people said the JC could not go high, okay, when TC goes high. But that assumption based on one thing, on the anisotropic material like cuprate. But this material, the great thing, I think I mentioned, but I didn't, I skipped through that slides, is that it's it's an isotropic material. Okay? Isotropic material, at least up to this moment, is a cubic material. So that means from fabrication point of view, it will be much easier. And also, in terms of the rigidity of the superconducting state should increase in this case. So we hope if we can prove that this is a superconductor, and it should be three-dimensional, and then the situation will totally change. Right.
Bob Schiffer used to tell me that that's the future.
Yes. Yeah. In fact, you know, because the heavy fermion, at the beginning, people were looking into it for higher TC because the gamma is so large. It turns out the TC was not that high, but it's a strongly correlated electron system. And this also, if H2S is proven superconducting, that will also change that picture. Because for this material, it's difficult to find the origin of the magnetism in it, you know. Because in all those heavy fermions, they have strong correlation generated by the F electrons, you know. But in this, even in the cuprate, we're talking about the D electrons, right, from associated with copper. So it has a strong correlation. But H2S doesn't have all those things. If it's proven, I think we have to change some of the thinking on high temperature superconductivity.
So are you saying that H2S could be a heavy fermion superconductor or not?
No,
I'm not an
I'm
expert
sorry, I
enough
should
to-
answer. No, in this H2S, I don't think it's heavy fermion.
Okay.
Yeah.
Thank you.
Yeah. Mm-hmm.
What's the situation on the iron?
Iron.
Was that expected at all? It seemed to me always rather unexpected. And is there hope there?
Yeah. In fact, that's interesting. Even though its TC was not that high, iron arsenide system, but people got very interested because of the iron, the presence of iron, and so large a proportion in it. And people try to use that to study the role of iron in superconductivity. I think from scientific point of view, it's very interesting. There are lots of ways you can manipulate it. I think then the iron solenoid, when it was discovered, and then when people, okay, let me come back. Because in all those high TC material, when they look at the Fermi surface, they ought to think about the electron-hole pairing, okay? Take an electron-hole nesting will play a dominant role. But in the iron solenoid, there was no hole pocket in the Fermi surface. And yet the TC was pretty high at the beginning already, maybe 40s or even 100 degrees. So all these things is not clear at this moment. Yeah. The more material discovered, the more complication it becomes, it appears to me. Yes.
I think one final question, we have a little bit over time.
The first one was superconductor, high TC2 superconductor, was from antiferromagnetic to superconductivity without going to paramagnetic phase.
Right.
Don't you think similarly in the future, same type of cooperative phenomena, that antiferromagnetic type of what is the T temperature, could be the type of temperature that high temperature superconductivity will also attain? This is
That has been the major ideas for people to look for, is talking about magnetic fluctuations that what you refer to, you know, from anti-ferromagnetism, produce this fluctuation to get it. So up to the H2S, and that's the path people have been following. But if H2S comes out to be a real superconductor, and that may change that, you know, that concept. Yeah.
Okay, thank you all. Let's thank our coach again.